In this video, I'm going to talk about parallax measurement and how to use it to measure the distance to the stars. Please take a moment to read the success criteria I plan to cover in this video. I know this might sound a little strange, but I'm going to talk about these 3 units of measurement. They're found in our data booklet, just like this. And first of all, we've got a light year. Now notice the units here are in meters. It's a distance. It's not a time. Very much a misconception with lots of people. It's how far light will travel in 1 year, not obviously how long it takes. A parsec I'm going to talk about a little bit later, but we're going to use it when we talk about using our parallax angles to make a distance out of it. And finally, an astronomical unit. This is kind of a sneaky way for us to have the average distance between the Earth and the Sun. It's closer in June than it is in December, depending on where you are. That could be summer or winter. So this is the average between them because it is an ellipse. But if we wanted to pretend it was a circle around the Sun, it would have a radius of 1.5 times 10 to the 11. In my video about calculating stellar radii, I use that to help with the solar constant to find the luminosity. So it's a hidden piece of information in my mind. So how are we going to measure something that we actually can't reach? It's not like I can use a measuring tape. It's not like I can have a rocket sent out there to these nearby stars. Let me give you an example using some distant stars and a closer one. Or, in my case, some Lego. So my distant stars are going to be the anglerfish and the T-Rex in the background. And my near star is my Lego lady with the Toronto Maple Leafs jersey. You can see at the front I've got my orbit marked with my extreme points with the little X's on the left and the right. And as I move from one edge to the other, look how the Lego lady seems to move in front of my T-Rex. Now she's on the left side, where before she was on the right. Let me do that one more time, and look how she moves in comparison to the T-Rex, our distant star. So if I talk about in the same idea, here is my anglerfish and my T-Rex. Here is my little Lego character in blue. And my circle that I would have had an X here and here. So notice I've got this angle of sight towards my distant stars, and when I'm at the farthest distance over here, I'm going to say I'm at June. Therefore, over here would be December. And I will get a parallax angle as measured from the center. So when I'm here, I think that I'm straight in front of my nearby star. When I'm over here, it looks like my star's to the left, or here, it looks like the stars to my right. And this parallax angle here from the center is going to be really important. So let's take a look here. I have a right angle triangle. Let me just highlight it here to make it stand out. This distance from the Sun to the Earth, that was the 1 astronomical unit that I talked about earlier. That would be the one side of my triangle. Here's my right angle. And now the distance from the Sun to the nearby star is what we're really looking for. I could be using this entire angle that I've measured and then divide by 2 to get the average for the P parallax. And notice I now have the angle and I have the adjacent side that I'm looking for and the opposite. So that would be tan theta, opposite over adjacent. Now, because it's going to be a very small angle, we can use our small angle approximation, saying tan theta is approximately the same as theta, as long as we're working in radians. And what we're going to do is we're going to use this equation that's in our data booklet. Now these brackets are telling you that this equation is only going to work if my distance is in parsec and my angle is in arcsecond. So let's look at these units in a little bit more detail. First of all, the reason we have a 1 here is this is for the astronomical unit. Remember I said I had tan theta, which would be opposite over adjacent. So tan theta is basically theta for small angles in radians, and that would be my opposite, which is 1 astronomical unit, over the distance we're looking for. Now, if I rearrange that to make it look like this equation, I need my distance, and it's saying 1 astronomical unit over my angle. Now, how they get this idea of a parsec is if I have a value of 1 here, I'm going to get my distance in parsec. Now, it says then, normally we would say radians. Well, that's not what we're looking for here to get a parsec. What we would need here, and our equation shows us, is my angle here has to be measured in arc second. So let's go back here. In 1 degree, I have 60 arc minutes. And in 1 arc minute, there are 60 arc seconds. So I could say 1 degree equals 3,600, 60 times 60, arc seconds. So if I have here just 1 arc second, and this distance is our 1 astronomical unit, then I will consider the distance from the star to the sun as 1 parsec. Now, 1 parsec is 3.26 light years. We can go back to our information in the data booklet and turn that into meters as well. So we're using this idea that when I look at the star in 2 different spots during our orbit, we see the closer star move in comparison to the distant stars behind it. So there are some limitations of this. First of all, in order to use our equation, we have to use a arc second. So 1 over 3,600 of a degree. That's really small. If it gets really small, any effects we have with those lines cause a big problem. If we're measuring them on the Earth, we can't negate the fact that the Earth's atmosphere causes some bending of our light. Just like we talked earlier with Snell's law going from, say, air to water. The same thing happens as it goes from outer space into the Earth. It might not make a big difference normally, but when we're talking about such small angles, it actually makes a big difference. And because of that, if our telescope's on Earth, we can only measure, no matter how accurate we think we are, up to about 100 parsecs. That's why you might hear in the news about space-based telescopes that are out beyond our atmosphere, and they can get an accuracy another 100 times better, so up to 10,000 parsecs away. To give you an idea about what that means in terms of the universe, our Milky Way, of which we're part of, is about 30,000 parsecs across. That's only a small part of the total universe. Now that we've gone through the theory, and before we get to the questions, has this helped you? Consider helping me out by telling your friends about the videos. Consider subscribing or liking the video. Thanks for your help. So let's do an example. Star A has a parallax angle of 0.5 arc seconds, and B has a parallax angle of 0.85 arc seconds. So let me just draw a quick picture. Here's the Earth. Here's one spot. Here's the other spot. And I'm going to say I've got 2 stars. Now, if I go here, and let me draw the other one in a different color. Pretend those are straight lines. Do you see how this angle here is larger than this one? And star A has an angle of 0.5, but B is 0.85. That means this one must be A, and this one must be B. Now, it says which star is closest to Earth and by how much. So let's put this into distances. So my distance is going to be in parsecs. I will have 1 over my angle as long as it's in arc seconds, which I have. And so this will be 2.0 parsecs. That is for A. And for B, the distance in parsecs, 1 over 0.85. That's going to give me 1.2 parsecs. And so the distance between them will be 0.8 parsecs. Now this question doesn't say what units I have to do, so I'm just going to leave it like that. Now, in B, it says convert the parallax angle of star A into radians. So I have 0.5 arc seconds. I'm going to walk you through how to do this. We have 60 arc seconds in 1 arc minute. There are 60 arc minutes in 1 degree. If I have 180 degrees, that's pi radians. Notice that I keep writing them in such a way so 1 arc minute is exactly the same as 60 arc seconds. And since they're exactly the same, this is like multiplying by 1. All I'm doing is changing the units. I'm writing them so that my units cancel out. Tops and bottoms are equal to each other, and so now I'm going to be left with radians. So I'm going to pick up my handy dandy calculator. I have 0.5 times 1 times 1 times pi divided by 60, and I'm putting this in brackets, times 60 times 180, and that's going to give me 2.4 times 10 to the power minus 6 radians. So definitely small enough for us to be using small angle approximation. I have no idea how to pronounce this name, so just let's go with it. The Hipparcos telescope was launched into space above the Earth's atmosphere. It measured the parallax angle for many stars. Give one advantage and one disadvantage of having a telescope in space. Well, one advantage is it's going to be beyond the atmosphere, so there's going to be less interference. A disadvantage is, well, I've got to get the telescope up there. And if something goes wrong, like originally happened with the Hubble telescope, it's difficult to repair. Antares is a red giant and one of the brightest stars in the night sky. The parallax angle for this star is .0059 arc seconds. Calculate its distance in light years from us. So, let's use our equation first. This will give us the distance in parsecs. 1 over our angle, if it's in arc seconds, already is. That's great. I don't have to do any changes. And if I pick up my handy dandy calculator, I get 169.5 parsecs. But now the question wants us to answer this in light years. So 169.5 parsecs is 3.26 light years. That gives me a total answer of 550 light years. So please take a moment and read the success criteria one more time. I hope you can now use parsecs as a measurement of distance. I hope you can say, yes, I can get the angles I need from parallax using our example with the dinosaurs and our Lego lady.